This is the story of the Plainview, a ship that could fly. In the late 1960s, the world was deep in the Cold War. Tensions between the United States and the Soviet Union were at their peak, and much of the conflict was being fought not with guns on land, but with submarines and warships hidden beneath the ocean. The Soviet Navy was rapidly advancing its nuclear-powered submarine fleet, giving them a powerful advantage in stealth, endurance, and reach. The United States Navy knew it needed an answer. Powerful as traditional ships were, they were slow compared to submarines. A submarine could slip away unnoticed, maneuver under the waves and strike unexpectedly. That imbalance demanded innovation. Enter the world of hydrofoils, a futuristic idea that promised to transform naval warfare. Hydrofoils are ships with wing-like structures beneath the waterline. When they gain speed, these foils lift the vessel's hull out of the water, drastically reducing drag and allowing the ship to fly just above the surface. The result: much higher speeds, smoother rides in rough seas, and greater maneuverability. The US Navy saw hydrofoils as the possible answer to the Soviet submarine threat. Unlike traditional ships, these vessels could dash across the ocean at airplane-like speeds, while still operating effectively in heavy seas. If equipped with sonar and anti-submarine weapons, hydrofoils could potentially hunt down Soviet submarines before they came too close. This was the vision behind the Plainview AGEH-1, a one-of-a-kind experimental hydrofoil launched in 1969. At the time, it was the largest hydrofoil in the world, stretching over 220 feet in length and weighing nearly 310 tons. Its massive foils, powered by jet engines, could lift it out of the water at speeds exceeding 40 knots, making it seem almost like a ship that could fly. The Plainview wasn't the Navy's first experiment with hydrofoils. In fact, it was the fourth prototype, following smaller test vessels designed to explore whether this technology could be scaled up for ocean-going warfare. Each prototype pushed the limits a little further, but the Plainview was different. It wasn't just a test boat. It was meant to prove whether large hydrofoils could realistically patrol the seas and counter Soviet nuclear submarines. But to understand the Plainview, we need to take a moment to explore the concept of hydrofoils themselves. The basic principle is deceptively simple. Hydrofoils utilize two key components: foils and a hull. The foils are submerged wings that protrude from the sides of the ship below the waterline. These foils generate lift in the same way an airplane wing does, except in 3 dimensions. As the hydrofoil moves through the water, the foil generates lift perpendicular to the oncoming flow, pushing the vessel upwards and reducing drag. The faster the hydrofoil moves, the more lift is generated and the higher it lifts the hull out of the water. The hull, on the other hand, is the main body of the ship. Unlike traditional boat hulls, which are designed to displace water, the hydrofoil hull sits relatively high above the waterline, offering minimal resistance. Hydrofoils come in various shapes and sizes, each suited for different purposes. Some are designed for stability in choppy waters, while others prioritize speed. What they all have in common is an ability to move through the water in a unique way. Now, let's get back to the Plainview. The construction of the Plainview was a marvel of late 1960s engineering. Measuring 222 feet in length and weighing approximately 309 tons, it was far larger than any hydrofoil built to that point. Designed by the famed naval architect John G. Hillard and constructed by the Seattle company of Puget Sound, this colossus of the seas incorporated advancements from the previous prototypes, while aiming to demonstrate the feasibility of large-scale hydrofoil operations. The ship's propulsion system consisted of 2 shafts, each equipped with a controllable pitch propeller connected to a gas turbine engine. This setup allowed for precise control over the vessel's movement, enabling it to operate efficiently in diverse conditions. Powering the Plainview were for General Electric LM2500 gas turbine engines, each capable of producing 4,500 horsepower. These engines drove 2 shafts, each featuring a ducted propeller with a diameter of 6 and 2 feet. This propulsion system granted the hydrofoil remarkable speed capabilities. The large propellers efficiently harnessed the power of the engines, allowing the Plainview to achieve speeds of up to 40 knots, about 46 miles per hour. When fully laden, such velocity was unprecedented for a surface vessel of its size, and marked a significant leap forward in naval engineering. The hydrofoil's control surfaces played a pivotal role in maintaining stability and maneuverability. Located at the rear of the ship, These surfaces comprised two pairs of balanced rudders connected to a single shaft, forming a V-shaped configuration. This arrangement facilitated quick and precise alterations in direction, enhancing the overall handling characteristics of the plane view. Additionally, the hydrofoil featured a pair of small trim tabs near its bow, which aided in fine-tuning the vessel's attitude in the water, ensuring optimal performance and stability across various sea states. Overall, the combination of powerful engines, efficient propellers, and well-designed control surfaces made the plane view a highly capable and responsive vessel. Its advanced engineering allowed it to reach speeds and maneuver in ways previously unattainable by conventional naval craft, showcasing the potential of hydrofoil technology for maritime applications. As you can probably imagine, launching a new piece of technology like this into the world was fraught with issues, and the plane view was no exception. Despite its impressive design and powerful engines, the plane view encountered numerous setbacks during its operational trials, highlighting the complexities of pioneering new technologies in naval warfare. One of the most significant challenges the plane view faced was instability at low speeds. While the hydrofoil exhibited excellent handling characteristics at higher velocities, maneuvering at slower speeds proved to be problematic. This instability manifested itself in unexpected movements, making it difficult for the crew to maintain control over the vessel, particularly in rough seas. Overcoming this hurdle required extensive testing and modifications to the hydrofoil's hull and foil design. Engineers worked tirelessly to find the optimal balance between stability and speed, striving to create a vessel that was not only fast, but also manageable in a wide range of conditions. Another major issue the plane view grappled with was cavitation around its propellers. Cavitation occurs when the pressure surrounding a propeller's blades drops below the vapor pressure of the water, causing the formation of vapor bubbles. These bubbles can then collapse violently, generating shock waves that can damage the propeller and reduce efficiency. Mitigating cavitation required careful tuning of the propeller pitch and engine power, necessitating continuous adjustments to optimize performance. Additionally, the plane view's propulsion system suffered from a lack of reliability. The hydrofoil's gas turbine engines, while powerful, proved to be susceptible to breakdowns and required frequent maintenance, impacting the vessel's overall availability and operational efficiency. This unreliability stemmed from the complexity of the propulsion system, which involved intricate components that were sensitive to various environmental factors. Overcoming these technical challenges was crucial for the plane view's success. The U.S. Navy invested significant resources into resolving these issues, recognizing that a stable, reliable, and high-speed hydrofoil could revolutionize naval warfare. Ultimately, the lessons learned from the plane view S trials paved the way for subsequent improvements in hydrofoil design and engineering, contributing to the advancement of this promising technology. So how did the plane view fare in its tests? It was commissioned on July 1969. Entering active service on June 1970. Initially based at the U.S. Naval Weapons Center in China Lake, California, the hydrofoil later shifted to the Naval Surface Warfare Center in Carteret, Maryland, where it underwent extensive trials. These tests aimed to evaluate its performance, handling characteristics, and overall suitability for anti-submarine warfare. The plane view's first test deployment took it to the Pacific Missile Range in the Bahamas, marking the initial assessment of its operational capabilities. During these trials, the hydrofoil demonstrated impressive speed and maneuverability, achieving speeds of up to 40 knots, which was remarkable for a vessel of its size. However, the tests also revealed significant challenges, particularly in maintaining stability at lower speeds. Despite these hurdles, the plane view continued to undergo evaluations, including anti-submarine warfare exercises off the coast of San Diego. These trials aimed to assess the hydrofoil's potential for hunting down enemy submarines, a critical aspect of naval warfare during the Cold War era. While the results were promising, they also highlighted the need for further refinements in terms of reliability and endurance. The final and most comprehensive trials took place in the Chesapeake Bay and off the coast of Virginia. Here, the plane view faced a series of rigorous tests designed to push its limits and identify any remaining issues. These tests included high-speed runs, maneuvering drills, and extended patrols, providing a realistic simulation of anti-submarine warfare scenarios. By the end of these trials, the plane view had proven to be a fast and maneuverable platform, capable of reaching impressive speeds. Its unique hydrofoil design allowed it to slice through the water with ease, making it an elusive target for enemy forces. Moreover, the hydrofoil's advanced engineering and powerful engines showcased the technological prowess of the U.S. Navy during the Cold War era. However, the trials also exposed the limitations of the Plainview's technology. Its susceptibility to instability at low speeds, coupled with the unreliability of its propulsion system, raised concerns about its overall effectiveness in anti-submarine warfare. Despite its impressive capabilities, these drawbacks hindered its ability to conduct the long-duration patrols and precise maneuvers required for successful submarine hunting. By 1978, the Navy had 4 hydrofoil prototypes under evaluation, including the Plainview. Collectively, they showcased remarkable advances in naval engineering, yet each faced the same question: could this technology realistically replace or even complement traditional warships and aircraft in the Cold War chess game? After years of evaluation, the Navy made a decision. The Plainview and its sister ships were decommissioned, ending the era of America's flying ships. Their service marked a significant chapter in naval history, demonstrating the relentless pursuit of innovation in the face of evolving threats. The story of the Plainview serves as a reminder of the challenges inherent in pioneering new technologies and the delicate balance between cutting-edge innovation and operational practicality. While hydrofoils ultimately did not become the primary weapon in the Cold War arsenal, their influence on naval engineering and the allure of this futuristic mode of naval warfare continues to capture the imagination. What do you think was the Plainview ahead of its time? Could the problems have been solved with more funding? Let us know in the comments. And don't forget to like the video and subscribe, so you never miss an exciting episode.